Amazing, thanks. Okay, welcome everybody. We can finally start. I'm Barnaba. I'm from the University of Klagenfurt in Austria. Today we are basically talking about simulating radar sensors, which is not a trivial task. So the first question is, why are we interested in radar sensors? Well, let's just stick to the automotive world, right? Because they find applications everywhere, of course. There is a bunch of tasks that we can do, right? We can do adaptive cruise control, we can do park assist, we can do blind spot detection. And, with respect to a camera, that would be the other main sensor that is used in automotive. They have some advantages, right? They work even if we have harsh environmental conditions, so we can still detect targets if there is rain, if there is fog, in the darkness. We don't need our own light source. They are easily coverable, meaning that we can mount them behind the bumper of a car. We can even mount them inside, let's say, behind the plastic cover of the cabin of your car. And again, with respect to a camera, they have the advantage that they keep privacy, right? Many people don't like the idea of being watched and recorded by a front-facing camera inside their own car. They have a bunch of other advantages. I mean, the list could be super long, but the question is also, why do we want to simulate them, right? Well, we want to simulate them because this thing is terrible. Because, of course, as any other sensor, we can, if we have a nice simulation, generate a huge amount of data in different scenarios, and this data would be otherwise difficult or expensive to collect in the real world, no? Also, the radars are a bit of annoying sensors in the sense that they have a lot of tunable and configuration parameters, a lot of variables. They have multiple outputs that the user is interested in having and having access to simulate. So it's not a trivial task, but of course, a simulation would help. Of course, there exist many automotive simulators in the field. Maybe Carla is the most famous one, is even open source. We also have the ones that are more physics-based, radio frequency-based. The problem is that all of them, even if they do provide a radar model, it's very limited. Often they only provide the final output of the radar. They don't really give the user access to the, let's say, to the raw time domain signal of the radar, which is where all the information, all the useful information is embedded, right? Often we don't have noise modeled in a nice way, especially the phase noise that I will talk about later. So the result is that they are often too optimistic, right? The simulation is too good. It doesn't really model how a real radar works in the real world. And maybe it's not a surprise, that it's also difficult to find in the literature validation of all the different type of radar output between, synthetic and real sensor. So the idea that we had is basically the following. We take one of these simulators, we take Unity, that doesn't provide a radar model, right? But it has a lot of very nice light modeling and material properties capabilities. We have basically our test environment is a parking garage next to our university. We basically make the model in Unity. And what do? We basically take the camera sensor model. Why? Because every simulator in the world will provide you with a camera sensor model. It's just the most used one, right? This camera basically will become our radar model because there is basically a correlation between, of course, the light wave and the radar waveform, right? So the idea we had is to each pixel of this camera will correspond a point in space that can be considered a radar reflection. The sum of all the points of all this radar reflection will basically construct the radar signal. The other thing we have to do is to exploit either the simulator's capabilities or some signal processing algorithms, some stuff that we have to do to make then the simulation realistic, right? So this is our main point. We want a complete and realistic simulation of radars. So this is a very high-level scheme of what is going on. Let's focus on the blue boxes here. This is everything that happens in Unity. We basically have our environment with the camera model. We get depth and intensity images. And we initially build a point cloud, right? This point cloud is then downsampled with let's call it a novel downsampling strategy that we have. Why do we have to downsample it? Remember I said before, to each pixel of the camera will correspond a radar reflection. In practically speaking, you cannot really do it because you have high resolution of the camera and that would be too slow, right? You don't have to take all these points. It would be computationally too expensive. And it's also not useful, right? Because real automotive radar have low spatial resolution, right? So it's not even needed to take all these points. So we downsample it. We initially downsample it, let's say, with a standard method, but then also on a, let's call it an intensity-based method. Cannot go into detail here. It's too little time. But basically, the idea is we want to mimic the radar signal. So we focus more on the points that have higher intensity, as a real radar would do. We can then input all our desired configuration parameters. We can take into account multiple input and multiple output antenna arrays. And of course, we don't have to go into detail about how the raw signal is generated. But I want to show you that there are a couple of parameters here that are very important, that are accessible to the user. For example, we have the Doppler frequency, which is related to the velocity of the targets. We have the azimuth and elevation angles. We have the distance of the target. And then we have a bunch of configuration parameters that the user can access to and select according to the requirements of the application, right? So the ADC sampling frequency, the carrier frequency of the waveform. And finally, there is also a relation that we have here between the intensity, right, obtained from the camera intensity, and the amplitude of this waveform, right? This is useful to detect targets. Then we basically perform all the standard radar signal processing algorithms. You can choose whatever you want if you're the user of this simulation, and you obtain the radar output, which is not only the point cloud, right, that we're interested into, but also the range Doppler map, where you have velocity information, and the range angle map. So this is still not over, because this is the ideal case, right? We still need to make it realistic. How do we make it realistic? There is a bunch of stuff that we can do. First of all, we start by modeling the transmitter radiation pattern of the radar. Basically, the thing is that, the radar transmits a waveform, but the gain of this waveform is not uniform along the entire edge of view, right? So the entire field of view, sorry. At the edges of the field of view, the gain is much weaker. So if we don't model this, this is what the intensity images will look like. So remember that we take everything based on intensity. So we would see here very strong reflections, right? That the real radar doesn't have. So we exploit something in Unity. Basically, this is a texture that to apply to the light source of the camera model in Unity. And by basically using this texture that we have to create beforehand, we can remove this effect and make it more similar to a real radar. We can exploit the ray tracing capabilities of Unity to model the multipath effect, which is also super important for radars. We can add thermal noise. This is the easy one because it's just basically additive white Gaussian noise. But the interesting thing is that we can add it to the time domain signal because now we have access to it. More importantly, we can model phase noise. Phase noise will be added as a phase term to the raw radar signal. So just a few words about phase noise and why it is important. This is generated, let's say, to make a long story short, it's generated by the non-idealities of the oscillator circuit that is in the transmitter that creates the waveform. And it has a very annoying effect to basically generate side bands in the range FFT spectrum. So this is basically a Fourier transform spectrum where you can basically detect the distance of the targets, right, when you do a peak detection. And the thing is, this is obtained in simulation, by the way. Here we have two targets, right? One is a building and one is a car. So if you don't model phase noise, so if you only have thermal noise, and the two targets are pretty far apart, there is no issue. But the amplitude of the targets decreases with the square of the distance. So when the car moves closer to the building, if you don't model phase noise, the car is still detectable because still is a good signal, right? But in the real world, you will not detect it. It will be masked under the phase noise bands, right, that have a higher amplitude. So it's super important to include this effect. Otherwise, again, the simulation would be too optimistic. And again, here, this is the same equation as before, just with the added phase noise samples that we can generate and the white Gaussian noise for the thermal noise. Good. So, okay. So we basically do all this stuff, and now we can validate the data, and we can check if the simulated data match the real sensor, right? So we have a bunch of experiments that I want to talk about. The first one is a parking side maneuver, meaning we have this is our ego vehicle, right? The radar is mounted here. We basically approach a car, first driving straight, then you want to turn, and you want to park next to the car. And what we're interested in is to check if we, of course, detect the car, but also if we can detect the fence that is here, right, the border, so you don't go outside of the building. We start with the range angle map. This is the real measurements from the real sensor. We can see the car in here, and we can see this shape, this arc, that corresponds to the fence. And we have very good reflections, and the car is a little bit weaker when we move straight. And again, when we turn, this is the car, and this is the fence. So in the simulation, we basically recreate the scene. We do all the stuff that I explained before, and we get very good resemblance, right, for the range angle map. Again, here we have the car, here we have, the fence, and we can really see the shape and the targets. Notice that we will see another scenario later that is even more complex, but this is a complex environment that there are a lot of reflection going on, right? We're not in a simple 1-2 targets thing, right? This is important for us. However, from here, it's really hard to see how the shape of this fence is, right? If you want to do like plane reconstruction, you need something else. So we also have point clouds, right? And in the point clouds, again, here you see that the real points and the simulated points that we obtain with our proposed simulation. And you see, especially when you turn, you really can see the shape of the wall, and you see the similarities between the points. One thing I want to mention, remember that the points of the radar point cloud are always fluctuating, right? So even if they're not perfectly overlapping, it doesn't matter. They're always fluctuating by some centimeters, right? So this is actually a very good accordance, and we see, again, the car and the fence and the car and the fence. This is another very, very similar example. We just now want to park between two cars driving straight, and we are interested in seeing the cars and the fence. And what we see, these are different time steps, right? So again, we can see the car and the fence. There are not, as you can see, the point cloud is really sparse. That's why the radar is annoying. The point cloud you get, unless you have an imaging radar, is terrible. But we can do a terrible point cloud as well. And another interesting thing is that when we get closer, both the real and the simulated radar cannot see the cars anymore, right? So this behavior is also correctly reproduced. Another experiment, this is now a driving experiment where we also have velocity data. So basically here we have a static scene, right? And the radar is mounted on this vehicle, and it drives back and forth in this parking garage. And again, this is a complex scene. We have a lot of reflections, a lot of stuff is going on. So you see how many targets we have, right? This is a range Doppler map. We can see the velocity. We have some equidistant targets. These correspond to these beams in the ceiling that are at 2.5 meters apart, right? The velocity is positive or negative according to whether I move forward and backward. And we see main reflections, right? The beams and the cars are very reflective, but sometimes we also have some smaller reflection with lower velocity magnitude. Again, we replicate everything in the simulation, and we are, we can still see that there is a very, very good resemblance, right? Of course, the model is not one-to-one. You see, like, it depends on how much effort you want to put into the modeling. The cars are not the same, the beams are not exactly the same, but the material properties are very similar. This is what counts. And also you see that we have both the equidistant targets, but we also have like these smaller reflections that are correctly modeled. Good. Also here we can see the point cloud. This is just an aerial view. So basically it's a two-dimensional point cloud that you would see from X and Z direction. And also, interestingly enough, the real sensor here doesn't have 3D capabilities. So the elevation angle is always 0. But with the simulation, with the same parameters of the radar, so to model the same exact radar and to add the 3D data, we can see that these equidistant targets are in fact corresponding to like 2.5 meters where we have the ceiling. And we can basically differentiate whether these targets are from the ceiling or from the floor or from the car or from some other structures like this one. Good. So to conclude, basically what we are able to do now is to have a simulation that is relatively fast in the sense that we get data at 1.5 or 2 hertz. This is possible because of all the downsampling part I spoke about before. The data that we get are sparse in terms of point cloud. They are noisy, but they are realistic, right? And they are complete. And we also show that we validate all the possible radar outputs. So we don't just have a few point clouds, right? We have range Doppler map, point clouds, and range angle map, and they all kind of agree with the real data. Okay, I would say that's it. Thank you.